The broadcast is now starting. All attendees are in listen-only mode.
It's gonna wait for 1 more minute. Okay, it's now noon, so let's get started. So, yeah, we have 33 attendees already, so let's get started with this. Welcome everyone to our webinar. Thanks to all of you for joining us today. I hope you are all doing great and staying healthy during these times. Thanks to the SPWLA International for the support to make this webinar possible, especially to Katerina Yared, the SPWLA for VP Education, and recently elected as President-elect for the upcoming board. For those of you who don't know me, I'm Javier Miranda. I'm the Vice President of the SPWLA Houston Chapter downtown, and I will be your host and moderator today. We will have our speaker bio and introduction, then David's presentation followed by a Q&A session. You can type in your questions or comments, and David will address them at the end of his presentation. So David Kennedy is a very well known in petrophysics and in our society. He began a career in the logging industry in 1973, following earning a Bachelor of Science in Physics at Georgia Tech. He entered the industry as a Schlumberger field engineer, and he worked there in California and Alaska for 5 years. David returned to school and earned a master's degree in physics and earth sciences at the University of Texas at Dallas, with further studies at University of California, Berkeley. He has worked in one or another capacity in research and operation at ARCO, Ohio, Mobil, ExxonMobil, Baker Hughes, Pathfinder, and Southwestern Energy. David has been a SPWLA member for 40 years and serves as VP Publications Editor, VP of Technology, and President. His major research interest has been formation, conductivity interpretation, and electromagnetic logging instrumentation. Before all of that, David served as a lieutenant of infantry in Vietnam, where he received both a Purple Heart and a Bronze Star. So please, let's welcome Dave.
Howdy, y'all. Welcome to my home studio in Montgomery, Texas. So we've gathered here together to talk about a gamma ray index shale volume transforms. And I want to acknowledge my contributors to this talk. And this is Dr. Quinn Passy and Elton Frost, former, well, still collaborators and colleagues of mine. So I like to call myself the skeptical petrophysicist because so much of what's presented is just presented and not proved. And I always like to have a proof of anything that happens. So in talking about gamma ray index shale volume transforms, I always wondered where they came from. Is it science or some kind of hoax? So let's continue to talk about that. Well, as you know, if you're working in the industry, that petrophysics welcomes all equations, no matter if there is a theoretical basis for them, no matter how empirical they are, they're all welcome. So why not these? So these are our 5 gamma ray transforms. So this is the gamma ray index. It's called I sub GR, and you know how this goes. It's the ratio of the difference between the log and the gamma ray minimum and the gamma ray maximum, gamma ray minimum. So it's a normalization of the gamma ray with a range from 0 to 1. On the other transforms, the one that this talk is really about, are the Larionov transforms. There are 2 of them. One is for what they call tertiary rocks. Here I've called them younger rocks, and the other for older rocks. Stieber's transform and Clavier's transform. And you would note that they are all 50 years old. So they're having a birthday. The usual presentation and how I was first exposed to them many years ago was, well, it wasn't PowerPoint then, it was overhead projector slides. But anyway, it was by means of a diagram like this, where you have gamma ray index as the x-axis, shale volume as the y-axis. The gamma ray index is the dotted black line, the dashed black line, and the transforms are these four curves. And you can see that the Larionov curves form kind of an envelope for the Stieber and Clavier curves, but the curves are not the same. And even in this presentation encrypted or from the internet, from GeoOil Corporation, you see this appellation old rocks and tertiary rocks. So we'll examine that. And we begin by looking at the original sources. So this is Larionov's book. The title translated from Russian is Borehole Radiometry. It appeared in 1969, written in Russian and behind the Iron Curtain. So it is not a readily available reference. And this copy that I have a picture of came from an interlibrary loan, and it's from the library in Göttingen University in Germany. We could not find a copy in North America. This is Stieber's paper. Stieber published in 1970, and notice that the paper is on pulse neutron interpretation, and the geography here was the Gulf Coast. And then Clavier and co-authors followed in 1971. And again, the subject of their paper was pulse neutron interpretation. And speaking of pulse neutron interpretation, this was the Dresser Atlas Neutron Lifetime Interpretation Manual. It has no date on it, but it does cite Larionov, so we know that it comes after 1969. And where does the citation appear is in figure 7, and you'll notice the curves, and it says here, after Larionov. So that is the citation. So someone at Dresser Atlas spoke Russian, was maybe was a Russian employee. At any rate, all of the service companies had these transforms available very early on. Larionov was the only publication of data. So we'll look at what everyone did, but let's begin by looking at the only published data. So this is figure 23, chapter 4 in Larionov's book. And on the right, you see data for carbonates, and we're only going to talk about clastics, so we will blank out the carbonates. And now let's take a look at the caption of figure 23. I studied Russian 3 times in my life and never learned it, but I know how to use a Russian English dictionary. And so word by word, I decoded the captions. And figure 23, the caption says the relationship of natural radioactivity, they call it Q sub pi, to heterogeneous sediment with clay. And this is a C sub gamma lambda. And gamma lambda are the first 2 letters of clay in Russian. And the C is like a percentage. So here is percentage of clay, and here is normalized radioactivity. Or actually, it isn't normalized. It just happens to fall between 0 and 1, because you see that some of the data, this is less than 0, and this particular point is greater than 1. So I don't understand everything about this data, but what I am able to understand by translating the caption is that for the field circle, these are for Paleozoic rocks. And how do I know Paleozoic? Because it says in the caption, Paleozoic sediments from the pre-Urals, which I take to mean the western slopes of the Urals, and central areas of the former USSR. So that would be Russia today. And the open circles are younger rocks. And it says in the caption, Mesozoic sediments from the southern USSR. So these days, there is no USSR. and this refers to Turkmenistan, Azerbaijan, Georgia, the Crimea, and so forth. And in figure 43, chapter 4, Larionov publishes his fit to the curves. So we typically ignore all of these lines and focus on this envelope, which is labeled as 1 in both of these figures. And by the way, I've flipped the figures to show them in the position that we usually plot them. So the caption for figure 43 calls the left data for Paleozoic sediments from the pre-Urals and Central European regions of the USSR, and B on the right for Mesozoic and Tertiary sediments from the southern region of the USSR. So the word tertiary appears only once in these captions, whereas Mesozoic appears in both captions. So leaving it a mystery as to why we have mistranslated that for 50 years. So this is the data compared to the trend that we usually fit to the data for the Paleozoic data. And you can see in the petrophysical sense, where we expect our data to have a lot of scatter, that this is a pretty good fit. And then we can put the Mesozoic and Tertiary data on top, and we see the appearance of the second predictive function, or the second trend line. And you see this trend line is not really as good as the first one. At least that's what I would say, because it seems as if the center of mass of the data is to the lower right of the actual trend line. And you could see that there's nothing special about this trend line that you could well imagine putting other trend lines through this data. The line is not by any means unique. So in terms of discussion of original sources, we move on to Stieber. Stieber did not publish his data. So what Stieber published was this curve. And the curve is what you would call not gamma ray index, but the complement of gamma ray index, 1 minus gamma ray index. And on the vertical axis is sand fraction, not shale volume. But Stieber did publish a formula that plots this curve. So here is the function that Stieber published. So it's a function of some parameter gamma. And Stieber does not give us a formula for gamma. He just gives us a definition: relative gamma rate of deflection, the fraction of shale to clean sand deflection. But we can decode that into this as a formula, and we would note that that formula is a gamma ray index complement 1 minus gamma. But 2 flips of the curve gives a familiar result. So if we flip the curve about a vertical axis and then flip it again about a horizontal axis, we see the emergence of the shape of the curve that we're talking about in this talk. And since shale volume is 1 minus the sand volume, we can plug in the variables, do the algebra, and come up with the transform from gamma ray index to shale volume that we know as Stieber's transform. What Stieber actually has to say about this curve is this relationship was developed by trial and error, and that's all we get. Pardon me. Clavier also did not publish a formula or data, so he publishes only this curve, and you can see as a graphical function, it looks pretty much like the others. You really have to go into detail to tell the difference. And what Clavier has to say about this curve: the use of the empirical chart was found more reliable than assuming linearity between gamma ray log and shale volume. So I want to pause for a digression regarding Larionov. What does Larionov actually say about age? So I don't want to leave you with the impression that I'm telling you something that you can't prove for yourself if you can find a copy of Larionov's book. So here is the caption from figure 23, and this is my translation of the caption with the words Paleozoic and Mesozoic. And where do they appear in the Russian caption? Well, here's Paleozoic and here is Mesozoic. And if you know your Greek alphabet, Cyrillic is kind of very similar. So if you read this, it's pi, alpha, lambda, epsilon, and then there's an O, and this backward E is pronounced Z. And this backward N with a hat on it has a sound value I, so you can sound it out. Paleozoic. And Mesozoic, here's the M-E-Z-O-Z-O, so Mesozoic. So you can see it's right there in the caption to figure 23. And the caption to figure 43 appears here, and here is the translation, and here is the correspondence between the translation and the words in the original, and here is where tertiary appears once and only once in association with the captions that describe the data in the figure. Well, does it matter? That's a question. Well, the tertiary, which by the way is an obsolete term these days, we would call it the Cenozoic, but begins about 65 million years ago and includes the Paleogene and the Neogene. The Mesozoic begins at 251 million years ago, and the Paleozoic at 542 million years ago. So there's a lot of time in there. But the Mesozoic endures for 186 million years, and the Paleozoic for almost 300 million years. So if we add together the Cenozoic and Mesozoic, we get about 250 million years, and the Paleozoic is 300 million years. So where is the oil that we're now burning in our engines and producing in our oil wells coming from? Well, it's coming from source rocks, and the source rocks were predominantly laid down in the Jurassic and Cretaceous. So this is showing the percent of global original petroleum reserves generated during, say, the Ordovician here on the Devonian, Pennsylvanian, Mississippian. And this is Jurassic, and this is Cretaceous, and this is Cenozoic. But note the scale, the 25% of our source rocks were generated in the upper Jurassic and 28% in the late Cretaceous or the Cretaceous at any rate. And so you add these together, 50% of our source rocks are coming from the Mesozoic. So does it matter? This is our last slide. It just matters if you care where we draw this boundary. So we have the boundary here between Cenozoic and Mesozoic, and the boundary between Mesozoic and Paleozoic, and that's 186 million years in there. And so do we want to put the boundary and divide the time this way, or do we want to divide the time this way? And it's going to be a matter of opinion. You know, it may not matter. So I leave it to you. Here's some snapshots of an animation of the Phanerozoic. And we're looking here at the late Paleozoic. And what I wanted to show you was where Larionov's data came from. So you can see the modern political boundary superimposed on these land masses. I guess this is called Pangea. At any rate, this continent here is called Baltica, and this is Siberia here. And this subduction zone is where the Urals will be, but the Urals aren't there yet. This is still a sea that is closing. Here's another subduction zone where the Southern Soviet Union will end up being. So the question is, if the Paleozoic sediments are from this region, where's the high ground? Because the radioactive material responsible for the gamma ray is being shed off high ground somewhere, and it isn't the Urals in the Paleozoic, because the Urals don't yet exist. Now we look at the Mesozoic. So here we are into the Triassic. These are where the Urals are. This is a suture zone where the Urals are. And now the Urals are higher than the surrounding, and they can shed sediments. Where would they shed them to? Well, this is the Tethys Sea. You can see the future location here of the Caspian and the Black Seas. This is Crimea, but the high ground here will be shedding to this coast, which will become the southern Soviet Union and southern Russia. So here we are at the beginning of the Cenozoic. Here's where the Paleozoic sediments are, and of course now they're well covered and underground. Here is the soon to be, or not soon to be, but eventually will become the southern Soviet Union. So here's Turkmenistan, Azerbaijan is here, Ukraine is here, and so forth. And the sediments coming into this region is coming from the high ground, and the high ground is most certainly to the east of the Caspian is the Urals, and to the west of the Caspian also the Urals. That's all I will say about it. What can we learn from Larionov? Well, the modern geography is, this is the former Soviet Union and modern Russia. Here is the location of the continental divide, that is the Ural Mountains. These are the oil fields in Central European Russia and in the southern USSR. So you can form your own judgments. But what can we learn from Larionov? Well, if you've been using the older rock transform for Mesozoic rocks, that doesn't correspond to Larionov's data. If your rocks are not located in southern Central European regions of the former Soviet Union, and you're using these transforms, can you be sure the rocks in your area of interest are radioactively similar to Larionov's? And if the rocks are more radioactive than, or pardon me, if younger rocks are more radioactive than older rocks for Larionov's data in his study area, would that apply to all rocks everywhere? Okay, that's what I wanted to say about Larionov. That's preaching, right? So call me Preacher Dave. So back to our transforms, and we ask the question, are these functions one of a kind? They plot in almost the same place after all. So the specialized version of the Larionov curves is, here is one, I think this is for the paleo, and here's the other, this would be for the younger rocks. And this is how they're usually presented, and they look, there's some similarity, but they look quite different, but actually they both derive from a formula that looks like this. So this is the generalized version of the Larionov transforms. It's a function of one parameter, A. So you can vary A. If A is 2, you get this transform. If A is 3.7, you get this transform. But they're both derived from that one formula. This is Stieber's formula, and it too can be generalized into a function of a single parameter. So I call this parameter B. And likewise, the Clavier transform can be generalized into a function of a single parameter. I call this one C. And you can kind of see how this works. If C is 0.7, and then C plus 1 is 1.7. So here's your 1.7. If you plug in 0.7 to this expression and do the arithmetic, you'll get that result. So we look at the generalized functions and we say, well, gee, these are a family of one parameter fitting functions. How different are they really? So let's take a look at how different they are. So here I'm going to plot our standard functions. So the two Larionov curves, Clavier and Stieber, and I'm going to animate the formula starting with Larionov as a red dashed line. So here it starts. Here's the red dashed line, and I'm varying the parameter A. When the parameter A becomes equal to 2, the dash curve will match the solid curve exactly. Pause a little bit so you can see that. But now here it is almost matching Clavier. And here it is doing a pretty good job of matching Stieber. And of course, it will match Larionov exactly. So let's move the red curve out of the way. And then next, take a look at Stieber's function. So we have to wait a while before it starts. I started in the wrong direction. Let us go back in the direction we want to go to. So Stieber's function is now approaching Larionov's function. Pretty good fit. And then Clavier's function, pretty good fit. And of course, it will fit the Stieber function exactly. And then we will be looking at the younger fit for Larionov. And now we move it out of the way. And finally, and this takes a while, Clavier takes a while to commence because of the way the function is written, but we should see it move right about now. It's moving and coming to Larionov. So this is Clavier. Clavier, of course, will fit the green curve exactly. Now let's take a look at how well Clavier fits Stieber. Pretty darn good. And then how well Clavier fits Larionov. So my claim is that we don't really need 4 functions here. Given the scatter in our data, we can't make any claims about the quality of the fit of any of these curves. We could just pick one function and vary the parameter in that one function to almost match all of these curves. Now to continue the discussion, the usual way of presenting this data is as I am showing here, but I want to present the inverse to continue our discussion of what is going on in this transform. So you would note that if you're looking at low values of shale volume, pardon me, I have to have a cup of coffee. For low values of shale volume, the gamma ray rises quite, well, relatively swiftly. But if we look out the shale volume axis, say between 10 and 20%, the rise is less steep. And as we look further out on the shale volume axis, the rise becomes progressively less steep. So what is this telling us? Well, it's telling us that when you have a little bit of shale, it's very radioactive. But when you have a lot of shale, well, it's more radioactive than this, but the rate of increase with an incremental increase in shale volume is much less. So the material itself is not, in some sense, as radioactive. So I'm going to show you the inverse transforms because we use them to plot the inverse curves. So you just do the algebra on the generalized functions, and it's very easy to come up with the inverse curves. And so I have plotted the inverse curves in this plot. So here are our 4 curves, and the red curve is a model, which you'll see more of later. I want to talk about Keith Katahara's 1995 paper on the gamma ray log response in shaly sands. So Keith was using the gamma ray index transform with shale volume, and so not silt volume, not clay volume, but shale volume, which is the sum of silt and clay fractional volumes, gamma ray log minus gamma ray clean, and gamma ray shale minus gamma ray clean. And so what does Keith have to say at the end of his paper? So I give you 2 of his statements. So he says if a strong gamma ray shale volume nonlinearity is actually a property of the formation, then either shale composition or sand composition or both must vary with shale volume. And the very last paragraph in his paper sort of reiterates that highly curved gamma ray shale volume relations, such as those of Stieber or Clavier et al., cannot be explained by shale distribution effects alone. If the curvature is truly a formation property, then it must be due largely to variations in shale or sand composition. So we look again at Larionov, and I just want to show you what this means. So I'm going to put some core photos on this diagram, and I want to emphasize these core photos were taken from the modern internet, not from 50 years ago, just as speculation as to what the formation looks like when you're getting this kind of gamma ray response. So this is a very low shale volume formation, but with a relatively high gamma ray and a high rate of increase of gamma ray. Here's my disclaimer, which I have just given you verbally. This is what a 50% shale or clay volume might look like. Actually, it's probably a little less. And then going up to almost 100% clay volume. So yeah, I realize this is about 50%, but you get the idea that I'm trying to illustrate is to somehow the radioactivity of these layers taken together is less than the radioactivity of an individual layer when it comes as an individual layer. So how can we explain that? Well, let's look at the radioactivity density and the Mohs hardness of three minerals that we find in rocks: quartz, clay, illite in this case, and zircon. And we'll look at the gamma ray measured in API units or calibrated in API units for quartz. The gamma ray value is 0. SiO2 has no radioactive material. So when you see a clean sand radioactivity, that radioactivity is not coming from SiO2, it's coming from uranium impurities in the rock matrix or from potassium salts dissolved in the connate water. Illite has a value of 87.5. It doesn't surprise us. We know that clay is radioactive, so here it is being radioactive. And then we look at our trace mineral zircon. Well, zircon has a radioactivity 3,773. I don't know where 0.15 comes from. Maybe it's 0.14 or 0.16, but this is the way they write it down. So you can see that a little bit of zircon will contribute a lot of radioactivity to a formation. That's the point. Now let's look at the densities. So comparative density is, we all know quartz is 2.65. Illite is slightly more dense, and zircon, however, is significantly more dense. So I won't say twice as dense, but 2 grams per cubic centimeter more than this mineral or this mineral. And finally, I want to discuss the hardness a little bit. So the Mohs hardness for quartz is about 7. Diamond is 10, and talc is 1. Quartz is about 7. Quartz will scratch steel and or some steel and not other steel, so it depends on the steel, which comes in different hardnesses, but quartz is roughly the same hardness as steel. Illite is soft, so it's somewhere between talc and gypsum, and you can scratch it with your fingernail. But zircon is 7.5, which is, and this is not a linear scale, 7.5 is quite a bit harder than quartz. So zircon will scratch quartz, but quartz won't scratch zircon. The significance is mechanical weathering. So zircon weathers quite well. It's a hardy mineral, and so you tend to find in a collection of sand grains, the zircon grains will have some large grains because they haven't been weathered down to the same extent as quartz grains. And the reason that I emphasize large grains is large grains with high radioactivity contribute a lot of radioactivity to a mix. So let's now look at a stream, a cross section of a stream with ripples in it. So we have a crest to the left and a crest to the right and a trough in the middle and a current flowing from left to right, carrying a suspended load of particles and a bed load of particles. And whenever the suspended fluid in the bed load comes over the crest of a ripple, the heavier particles are going to tend to congregate in the trough of the ripple. So this is called, if you're prospecting for gold, you call this a placer deposit. But any heavy mineral will end up at the bottom of a ripple. The lighter minerals remain suspended in the suspended load, or they hit the rising slope of the ripple here and become part of the bed load again and continue on up. But the point is that zircon will become concentrated in the troughs, and the remaining fluid and bed load and suspended load will be depleted in zircon. That's the point I'm trying to make. And you can see this phenomenon happening. This was a placer deposit, I call it, formation following a rainstorm in a gutter near your house. I say my house is where I actually took the picture, but you can see the crest of the ripples, and in the troughs is this dark material collecting in those troughs. And I'm not claiming this material is zircon, but I'm illustrating the point. So you get the idea. So how does the zircon lamination, silt lamination deposit? Well, here's a ripple bed. So if our scale is the same as in the previous diagram, maybe that's 1 centimeter, and at the trough behind each ripple, this heavy material, zircon containing, is accumulating, and the ripples will migrate to the right, which is downstream, leaving behind the heavy material as a layer. So we have a lamination where zircon is concentrated and a suspended in bed load where zircon is depleted. So what we need is to use these facts and develop a physical geological explanation, complete with a cartoon explanation. So here is a cartoon explanation. This one I've lifted out of the internet, but we need our own special cartoon explanation if we continue with this. And what I wanted to show you, though, what this could illustrate is the zircon concentration as a function of distance from the source is diminishing as we head toward the basin. In the highlands where the sediments originate, the concentration tends to be high. And as we move out into the basin, and especially out into the pelagic part of the lake or the ocean, the zircon is not in the lode anymore. Only clay remains in the lode. And so our physical explanation, that is our theoretical explanation, would look something like a Joule-Strom curve. I don't know how to pronounce this, but I'm going to call it Joule-Strom. And you can see that it plots diameter in millimeters on a logarithmic scale against velocity in centimeters per second on a logarithmic scale. And it is showing how or under what circumstances a particle in the bed load would, or the suspended load, would be deposited. So for example, if you're at 10 centimeters per second and you're at about 1 millimeter diameter, then you're being transported as bed load. But if the velocity goes down to 5, then you get deposited. So that's a theoretical curve. Here I'm showing where sand and silt would plot on this grain size scale. I know you can't read this, but this is coarse, medium, fine, and very fine. And it repeats coarse, medium, fine, and very fine. So here's the Joule-Strom curve. And the reason I'm repeating it here is in this particular representation, there is an inset that says that the flow depth is 1 meter. Flow depth is 1 meter. So we know that if this curve came from experiment, then the water depth was 1 meter. But it doesn't say what the particle density is here. Well, particle density obviously has an effect. So if we assume that these curves were for something with a density of quartz or other minerals like limestone calcite is approximately the same density as quartz, as we saw that illite was, then the deposition that takes place is going to take place along a line like this. So we repeat this line for the density of quartz, but we consider, say, a particle with a 2 millimeter size at 10 centimeters per second is going to deposit if the flow rate decreases at all. Sorry. But if we have lines for zircon on this same chart, these lines are going to be higher, so that, for example, the zircon won't or will deposit at any flow rate less than 55 centimeters per second. So if we go down to 54 or 44, 34, zircon is going to deposit while quartz is still in the bed load or the suspended load. So again, that leads to the conclusion that we can deplete our zircon supply. So here's the proposed model. The rest of the talk is about my proposal for a model. And if you wanted to argue with this model, that's fine. That's kind of why I do these things, to get arguments started, because understanding comes out of people arguing about how things work. So here are our observations, or it's a cartoon of our observations of gamma ray index versus shale volume. And this is the physical model that I am going to quantify. So in this physical model, we're looking at sand fraction from 100% down to 0%, and shale fraction from 0% down to, or over to 100%. Our model shale is going to be 60% clay and 40% silt. And our silt is going to comprise two fractions, a quartz fraction and a zircon fraction. And these numbers in the brown give the percent of the silt that is due to zircon. So at 10% shale volume, meaning that we have 90%, pardon me, at 10% shale volume, then the silt fraction is 90% zircon and 10% quartz silt, and so forth for all of these numbers. So I'm going to quantify that cartoon. So quantifying the, and I call this the dual silt model because I use two components of silt. So this is what the volume fractions would look like. Here at 0% shale volume, you got 100% sand. At 100% shale volume, you've got 60% clay and 40% silt. And I like to colorize this model. It's kind of easier to see when you colorize it, but this is the model that we're thinking of, except we're going to give now two components to the silt. So how are we going to assign those components? Well, I'm going to start with a gamma ray index formula and decompose it to get a gamma ray log value in terms of gamma ray shale and gamma ray sand, so that I can pick a gamma ray sand and a gamma ray shale and produce a gamma ray log as a function of those two parameters that I pick and the gamma ray index. So when I look at when I do this in this model, I have picked a gamma ray sand of 15 API units and a gamma ray shale of 120 API units. So how this works is at 0% shale, there is no clay, and the gamma ray value is 15 API units. And as the sand volume diminishes and the clay volume increases, then the radioactivity due to sand diminishes down to 0. On the other hand, the gray curve, this is the radioactivity due to the clay component, starts at 0 shale volume and increases to 120 API units at 100% shale. And the total radioactivity due to the sand and the clay component is this green curve, which is the sum of the yellow and the gray curve. And the difference between the observation, and my observation is going to be Stieber's model. I just picked it arbitrarily. I could have used any of the others. Is the difference between the observation and that green line is called the excess radioactivity. And so I call it, or I assume that it's all due to zircon silt, and it's variable. So it's going to start at 0 silt volume. It's going to end at 0 at 100% shale volume. And in between it will rise to a maximum and then diminish. And to do this, both the volume of the zircon silt and its radioactivity have to vary. So how does the radioactivity vary? Well, this is the apparent radioactivity of zircon silt, and this is measured in API units. And we saw that zircon is very radioactive. Remember, it was 3,773 or something like that. So now we're looking at the radioactivity of the fraction, And as the fraction varies, the radioactivity, and I'll show you in fact, I'll show you the formula right now. The formula that I use to compute these blue dots is this formula, which is the excess radioactivity. So that's that distance as a function of shale divided by the volume of silt. And so that gives me the zircon silt radioactivity. And it diminishes as shale volume increases, because our assumption is that the volume of zircon silt decreases as shale volume increases. So we can plot those 9 curves. We can't plot the curve here because it's divided by V silt and we can't divide by 0, but we can fit a cubic polynomial to this curve and extrapolate to 0. And when we extrapolate to 0, that means that all these x's are zeros, and what's left over is 500.09. So there's 500.09. That is our radioactivity of zircon at that point. And just to show you that there is a model behind this, I won't go over all of these equations. I just want to show you they exist. So here is gamma ray index. Here's gamma ray index solved for gamma ray log. We make the assumption that gamma ray log is the volume weighted average of sand, silt, and clay, and that the volume of the silt is the sum of zircon silt and quartz silt. And that for this particular model, I have elected to make zircon silt the only radioactive component, and quartz silt will have no radioactivity. So here is my formula for, or definition of, gamma ray excess, and that's what we're trying to match. And the gamma ray value as a function of V shale of the zircon silt is given by this formula, the excess divided by the fractional volume of the silt. And the fractional volume of zircon silt is given by the radioactivity of the zircon as a function of shale volume divided by the maximum zircon radioactivity. So those are the formulas that I've used, and using those formulas, I can modify our dual silt model and put in this gray curve, which is the boundary between the quartz silt, which appears above the curve, and the zircon silt, which appears below the curve. So here it is colorized. So here's our zircon silt. So this zircon silt fraction is accounting for our nonlinear radioactivity in our transforms. And again, I'm not going to talk about this except to show you there's a more complete model description, which will appear in the paper that I will write about this topic very soon, actually. And so I'm going to sum up now and say what's needed is a confirmation by sedimentological theory and observations. So we need a cartoon model of our deposition, and we need a quantitative model of the deposition that includes not only quartz, but also zircon in order to sort of validate this, this model. So these are my closing remarks. Now we have reached them. And these might seem kind of weak closing remarks, but okay, it is what it is. In the future, let's state Larionov's rock ages correctly. So we will have to overcome a lot of history and culture in changing that. But I've shown you what Larionov said, so why don't we use that? And secondly, we need to develop a physical model for the gamma ray index V shale transforms. I've proposed one. If you don't like it, argue with it and propose a different one. And finally, and I have put this in, it's grayed out because I'm going to put it in an appendix, but we could replace the 5 standard transforms with a single transform based on Bezier curves. So I did have references. Here they are. And here's what I wanted to show you in the appendix. So do we really need these 4 or 5 transforms? Well, here is a second order Bezier curve. Second order means that the parameter in the curve is squared. And these are parametric curves for the 2 coordinates, IGR and V shale. in terms of this parameter T, which varies from 0 to 1. So this will give you, you plug in a value of T, you get out a value of IGR, and you plug in the same value of T here, and you get out a value of V shale, and that gives you a point on the curve. And then X1 and Y1 are free parameters that you pick to match the curves. And at this scale, it is, you could say it's hard to see, but it really isn't because the curves overlay. So the point X1 and Y1 is shown by the golden X. So there's the golden X. And the Bezier curve fit overlays in these cases. So this is Clavier, this is Stieber, this is Larionov younger, this is Larionov older. And you can see that the fits are really good. And I'm just going to show you 4 more images and then we'll be done. But this is a single 2-parameter fitting function that would fit all of these curves if we wanted to keep and use these curves. So here is Larionov's Paleozoic. So you can see where the X and the Y are, and you can see the fit of the yellow curve and the red dash curve is almost perfect. And Larionov Mesozoic and Tertiary, again, an almost perfect fit. Stieber, again, an almost perfect fit. And Clavier, an almost perfect fit. And with that, I'm going to leave you with this presentation, gamma ray index, shale volume transform, science or hoax. So you decide.
So Dave, thank you for your excellent presentation. Now we are open to questions, and I have one here for you. Is do you have a copy of the Larionov paper? I've tried to find it, but never able to find it.
Well, it isn't a paper, it's a book. And these graphs come out of chapter 4. And it is a very difficult to find reference. I'm adjunct professor at Texas A&M, so the library works pretty closely with me if I ask them to help. And they did an interlibrary loan search and found one and only one copy in, I'm going to call it the Western world, but North America, South America, Europe, found only one copy, and that was, I showed it from the library and at Göttingen in Germany. So no, there is no place to get a copy of the reference unless we can somehow get permission to just Xerox it and publish it. But we would have to ask permission. It's still copyrighted. By the way, it is still available in Russian, so you could buy it in Russian from the publisher. The publisher is still in business, publishes thousands of technical books. So maybe your company would get it for you. I understand that De Goyer Magnaten has a copy, is that, or at least a copy of a copy. Xavier may know the answer.
Yeah. I will check that for sure. I'm not sure about that, but I will check that for sure. Let's see what else we have here. Well, others have been comments about thank you for sharing. Thanks for sharing the figures and your presentation. Thanks for sharing your work. Any other questions here? We have 48 people now connected, so probably thinking about that. Let's see. There is a comment here. Okay, let me read that for you. As a gamma ray index is not a clay volume indicator, but indicates terrestrial input, and neutron density can indicate clay volumes more directly. Can you speak about the usefulness of index of gamma ray or gamma ray index?
No, I mean, I agree with the comment. It's just, as we know, many people and in appropriate situations will use gamma ray values as a clay indicator. In fact, they will use every clay indicator that their data will support, and then typically pick the minimum. I don't know what kind of scientific procedure that is, but you will recognize that that is what we do, and our software has those options. At least the software that I use has those options. So you calculate every shale indicator known to man, and then you splice them together to get the minimum shale.
Okay. There is also one comment here. Question: care to comment about use of V clay versus V shale while we are on the subject?
Well, yeah, I can only comment on it, and the comment would be, I don't know, snide remarks. It just is amazing that 50 years after we started this this identification of shale volumes and distinguishing between shale and clay, that we still aren't clear on it. Shales are a mixture of silts and clays. Hardly any shale is 100% clay, and the average tends to be around 60% clay and 40% silt. And you know, which you plug into your Shaley sand saturation equation is a matter of who trained you and taste. But I really can't give you, you know, a magic bullet for doing that.
So there is another question.
But I would, you know, if we still have an audience, I would encourage the audience to start an argument about this so that we can get some papers written and maybe get it settled.
Yeah, I'm sure that this presentation will trigger a lot of arguments and a lot of good work from especially from our younger generation. So there is also another question here. Have you tried using the dual silt model with real data and compare the result with the traditional gamma ray index, Larionov, etc.?
I'm sorry, Xavier, I didn't quite understand all of that.
It says, have you tried using the dual silt model with real data and compare the result with the traditional gamma ray index?
Oh, no, because the dual silt model is kind of brand new. I mean, I'm still working on it on a daily basis, so I haven't compared it to data. And what data? So actually there are two data sets, well, three. Larionov gives us two, and Passy or Bouillon and Passy give us another one. It's a very abbreviated data set, but they do plot the data on the same kind of plot. And you know, it would be nice to answer this question with data if someone would spend the money to do the study. And I don't look, it hasn't happened in 50 years, so I'm not looking for it to happen in the next 50 years either.
So there is also one here. Thanks for sharing them. As petrophysicists, do we really need a V shale to correct total porosity into effective porosity? Since effective porosity may means different things for reservoir engineer, core analysis, etc.
I think I just heard that effective porosity means different things to different geo people, engineers, geo scientists. I really don't know how to address a question about effective porosity. I tend to prefer to use total porosity except the lower water saturation, or pardon me, the higher water saturations. That's, we know what they mean. I'm going to dodge that question because I don't want to answer a question about effective porosity.
There's a big Pandora box that you could be opening. Right. Yeah. So the last question before we close out is, have you compared your model and results with the XRD data?
Well, I don't have a source of data. So the answer is yes and no. I have a correspondent in South America who consults with me, and he sends me data, and I take a look at his data. And we tried to use XRD data and log data to generate sort of a synthetic data set. But for the particular data that we had, it did not work. So does that mean it would never work? No, I don't think so. I think it will work in most cases. But I've only tried it on one and only one data set. So, you know, I am available for hire. Here's my phone. Let me turn that off. So if we wanted to do a study, you can ask me to come to your place and do a study with you. Maybe we can figure something out. I mean, if you have data. So I'm not talking about core data. I'm talking about SRD, maybe log image data, some way to get a shale volume estimate and compare it to clay from XRD.
Okay. Well, I think that we run out of time. There are still some few comments and questions. Probably you can address them. I mean, you can direct your questions to Dave Kennedy. I'm sure he's very open to continue the discussion for this event, for this subject. And for now, I would like to thank you all. Thanks, especially David, for taking the time to prepare your excellent presentation. Now I can see why you have been involved in education for so long. And it's a pleasure to have you here. And thank you for your presentation again. And thank you all for attending.
Thank you very much.
Thank you, everyone. Bye.